our next wonderful speaker, Anna-Katharina Wickert, who's a PhD student at the, excuse my pronunciation, Technische Universität Darmstadt. So in this talk, Anna will introduce and explain 6 very frequently discussed problems for insecure crypto usages and demonstrate secure solutions for common use cases. So very excited to have you. Welcome, Anna.
Thanks for having me. You should see my slides now, correct?
Yes, I see them.
Great. Today I will talk about, first, thanks for introducing me and having me today here. I'm very pleased to be here. And today I will talk a bit about some crypto fails and how Go can help you tackle them. So who am I? As Angela introduced to you already, my name is Anna-Katharina Wickert, and I work currently as a PhD student at the Technische Universität in Darmstadt. And I'm in this community, or partly because I also organize a local chapter of the Go user group in Frankfurt. That's in the middle of Germany. You can also find me on Twitter. So what is this talk about? So first, I will introduce a bit the motivation why you should care about crypto. Then I will show you 6 common misuses in the wild. Then I asked myself the question, because they are in Go and Java, can we repeat all of them in Go with the standard library? And then I will shortly show you 2 secure code examples. So you probably all have heard about crypto fails, and if not, I will show you now 2 examples. In December 2000, there was a security notification for Schneider Electric for the car charging station, and you could attack them because they hard-coded their credential. You can imagine a hard-coded credential like putting your key on the street or posting it publicly on a board so that everyone can see it. And if you do that for sensitive software, you can imagine everyone who sees this key can take it and enter your house, if it's your house key. And that's an issue. But may you say, yeah, that's in some other software, and that's not Go related. And I'm sorry to tell you, no, that's not true. You also have crypto issues in Go software. For example, this issue was reported back in January this year, and it was part of a password manager in Golang. So you can imagine having a vulnerability in there could mean that attackers perhaps can get your credentials or your passwords stored in this password manager, which is a kind of issue. So this vulnerability itself had a medium severity, but still, I think, and it's also fixed because it should be avoided. So why this one happened? It was because they only used a part of random salt, which is like, imagine it like some randomness you're putting to your primitives, and they don't use it fully, but only used a part. So they only used it half, which led to this vulnerability. So perhaps you say, yeah, there are some misuses, and she looked them up, and that are the only one. No, I'm sorry. I'm really sorry to tell you that it's not true. So at least studies suggest this. So there were studies which were conducted in academia, mostly on Android apps, so Java, and also some in industry, who show that between 60 to 69% of the applications have at least one kind of crypto misuse, meaning that of, I don't know, X crypto usages, at least one was insecure. And I think this number is kind of alarming and also a bit of demotivating, depressing, to be honest. And yeah. And today, and the 6 misuses presented in one of the first papers, and which I have seen discussed a lot, and which are also related to the 2 real fails I have shown you at the beginning, are the following. So you shouldn't use a specific mode. Mode what? Okay. Okay, something about an EV. No clue what is this. Okay, constant encryption keys. We had that. You also shouldn't use constant salts. Then they talk something about iterations. Oof. And you shouldn't seed something with secure random. Okay, that sounds a bit complicated if you have never heard about it. Must admit, and we are looking a bit into all these in the next few minutes. So, ECB mode is a block mode. So, when you encrypt a message, you have to split this message into multiple blocks. And to combine the blocks, you have a mode. In this case, the ECB mode, take each block, encrypt it, and go to the next block and encrypt it. And at this, the same part of the message or the same message will always look the same. That's also the reason why these beautiful party gushers look kind of all the same. You can see that there was a gopher party ongoing, and your chef knows, or your boss, sorry, it's a false friend in German, sees that you were on a party and not working. So that's not good. And back to ECB, and that happens because each block is taken, encrypted, and then the next block is taken. I mean, of course, don't see the image completely, but you see enough to get the image or have the possibility to further attack this. So now some folks, genius, have created another mode, and they thought, like, if we have to combine these or change these blocks, we just put a random block in front of it and combine the first block with this random block, and then we get the encrypted block and combine this first encrypted block with the next encrypted block, so that we not come into the failure of before. Yeah, but this assumption only holds if you change your first random block. If you don't change it, you see, okay, you don't see that good in this image, I'm sorry. But if it's always the same at the beginning, you don't win much. Now, talking a bit about a constant encryption key. As mentioned, you actually want that your message is secret, but if you put your key in some GitHub repo or somehow in public, somehow your message is open, because people who see your key can also encrypt it. And that's not good. That was kind of a lot, and I tried to ignore all the heavy mathematics behind crypto, and now the reminder 3. So a constant salt And if your salt is constant, the effect is similar to having no constant. And yeah, as discussed, if you have some primitive, or if you want to do some randomness into it, such that your data isn't predictable anymore, and you have it constant, it's kind of like putting your key on a place or your salt in a place where everyone can see it and just has to know where it is. For the 1,000 iterations for password-based encryption, the rule is very simple, kind of. For the password-based encryption, you need several rounds to be secure. And for now, a number which is kind of agreed by experts on which you should have at least 1,000. And thus having an iteration count of, I think, 19, as I have seen this week in some code, simply isn't enough to be secure. So what the 1,000 is doing, it's just increasing the computing cost for an attack. And that's enough if you increase it from 19 to 1,000 for at least normal applications. And again, we have a static seed as like a constant seed. Secure random. If you want to generate random in computers, you often have to feed a seed into it. And if you always put the same constant into it, or if you're random, or it will result in kind of the same mesh outputs. And thus, counter-error, it results in a constant key again. Now, that was kind of a lot, and I hope I don't have lost you all. And these misuses were from, I say, mostly Java, or at least they're frequently discussed in Java. Okay. I mean, the idea behind it, they also apply to other languages. And I wondered, okay, is Go doing a better job on this than Java? Because all the misuses I discussed are really easy to misuse because of the design of the JCA. Some of these decisions are due to legacy because Java is very old, but that also shouldn't apply to Go because Go is newer. So I looked into it. And yeah, so first I only looked into the Go standard library. The two misuses for password-based encryption are not covered by the standard library, but Go has very good libraries to doing this job. But because of the limited time, I only looked into the standard library. So what's really cool about Go, the ECB mode, the one with these cool cover party images, these are not allowed in Go because you can't use them. They are simply not implemented. I repeat, they are not implemented. And there were also discussions where people ask, hey, can we have ECB mode because I need it for this and this reason? And the answer was no. If you really need it and know what you do, you can implement it by yourself. And if you can't do it, keep your fingers away. And even then, keep your fingers away, kind of. And then in Java, you can feed a seed into secure random. That's something which you can't also do in Go because you simply call the function and you don't have to care about how to seed it for you. The API is doing this job for you, which is, I think, kind of cool, isn't it? And then, yeah, checking for non-constant encryption keys and non-random EVs, it is kind of the same because it's a constant implemented in your program. For CBC encryption is something which is not covered by the library, which is okay, but you can cover it with analysis. Now, that was a bit, and now I want to share 2 code examples on how to do it right in Go. I've talked a lot about how to do it not right and tried to give you a first impression of some crypto stuff and how you can fail on it and why it's difficult to do it. Now I want to show you right ones. So to create a secure random number, the first and the important thing is check that you have imported the crypto.rand and not math.rand, because these 2 packages are different. Crypto.rand or /rand ensures you that you get the crypto random number generator and not a mathematical random number generator, which has not that high standards on it. And if you would use the math.rand, you wouldn't get secure random numbers, at least to cryptographic standards. And then the remainder is kind of straightforward. To get a new random number of length, you simply have to pass the byte in which you want to have the random numbers. Oh, not, sorry, this is sort of function. And you simply create an array of your length, byte array. Then you read from the cryptographic source, which is rand.reader.random. And then you can return it. No. Oh, sorry, I have to take a nip. Now, encryption. I've talked a lot about modes which you shouldn't use or with which you should be careful. In this example, we will use another mode. Keep this in mind and use it if possible, which is the GCM mode. And this is cool because it allows you or enables you that you have confidentiality and authentication of your messages. How you do this in Go, sorry. You first create a block and create a new cipher block, which you do with IS new cipher, and you pass your key, which is a byte array. Then you choose GCM as your block mode. As I mentioned, use this. Don't use any of the block modes I mentioned before, except you have to use them because it's some company's restriction or you have to follow some standards. And that's as simple as calling cipher.new GCM and pass your block into it. And then you get a new GCM. Of course, you can get an error, but let's assume we have no error. Then we create a random nonce. We create the random nonce in the same way as before. We create the byte array with the size of our GCM nonce. And then we call io.readFill with rand.reader and the byte array we created. With this, we have the random nonce. And then we can call gcm.seal with our nonce and the plaintext. And this will encrypt our plaintext, which is, I think, also kind of forward. It's just 4 simple steps, and most of the code is due to handling your errors. Now, if you're interested in this, you can ask your question now. You can also take care of or use existing resources. There is one really cool repository called CryptoPaster, which has Go code about secure implementations, like also GCM example. A Slack channel, which I found kind of cool, which is called Crypto. You can find a lot of people posting crazy and simple and pragmatic Go stuff, crypto related stuff there, and also non-Go related. Very interesting. And from what I have seen, the questions there are always answered very good, and there are very good discussions. And I give a hint to it. You have the API on the one hand, which can help you prevent misuses. And I think the Go Crypto API is already doing a great job into it. But you can also make use of static analysis to identify your misuses. And GoSec is one of these linters analyses. And beside these existing awesome resources, you can also check out the examples, the 2 code examples, and the slide deck in my repo talk. And with that, I want to finish my talk. And I want to repeat to you, don't use ECB if you don't want your party pictures from last weekend to be shown to your boss. Generating new random and also encrypting with GCM in Go is very simple. It's just a few lines of code. And the Go standard library is doing a great job in helping you to prevent some of the crypto misuses. Thanks for your attention.